everyone. Our team consists of Bertran, Louis, Chek Wei, Zi Quan and myself, Jie Shi. We will be presenting on concurrent processing on graphs, the challenges of it, and how Apache Giraph addresses these challenges. So firstly, what are graphs? A graph is a pictorial representation of a set of objects, where some pairs of objects are connected by links. So as you can see, these pairs of objects are nodes, and they are actually termed vertices. And the links connecting the vertices are called edges. Two vertices are considered as adjacent if they are connected to each other by an edge. In the following example, C is connected to B, hence is adjacent to B, and B is adjacent to A, and so on. A path represents a sequence of edges between two vertices. In the example, you can see that A, B, C, D represents a path from A to D. Now that we understand more about graphs, let's talk about why is it that we use graphs. So firstly, graphs can be used to discover relationships between data, especially since secondly, relationships can be easily represented through edges and vertices. In the real life example, we will be using Google Maps. So in Google Maps, in order for it to provide users with the best route from the starting place to the destination, it uses roads as edges, intersections as vertices, and hence you can see that there's a variety of paths available for the users to choose from. So actually it's very necessary to have concurrent processing on graph structures in order to find the best route users to travel on.
Before we delve deeper into Giraph and graph processing, we first need to know how Hadoop and the Hadoop Distributed File System HDFS works. In a scenario where we have a file of 300 MB and we want to store it in a HDFS, it will be divided by the block size and stored on multiple data nodes. In this scenario, block size will be the default value of 128 MB. Next, we have to understand how to read a file from the HDFS. To read a file from HDFS, the client will have to first interact with the name node to retrieve the address of the data nodes where the data is stored. Then, the client will proceed to connect to the data node to retrieve the data. And from now on, we will take it that a read-write action on a data node will cost 1 I/O, and for simplicity's sake, every I/O will take 1 second. On HDFS, processing of data is usually through MapReduce, and it is designed to perform concurrently, so in this case, it is 3 I/Os, but since they can be performed in parallel, it only takes 1 second. Again, to simplify the scenario, one MapReduce step would take 1 second. However, the challenge comes in when what we are processing is actually a graph where the relationship between nodes is critical. Now, imagine we are given a graph consisting of websites and their links to each other, and we have to calculate their page rank using the Google PageRank algorithm. And we want to give an incoming link from a website with higher page rank a higher weightage during calculation. This means that every website's page rank is dependent on the page rank of the sites that link to it, causing a spillover effect. Next, we assume that the calculation of page rank is done through the Hadoop MapReduce. This makes the problem challenging because we would have to perform the MapReduce step multiple times before it converges into the final page rank values, and it will incur extensive I/O costs.
Now that we understand graph structures, let us take a look at the challenges of concurrent processing of these graph structures. The data in graph problems are typically unstructured and highly irregular. Similar to the difficulties encountered in parallelizing a graph problem based on its computational structure, the irregular structure of graph data makes it difficult for concurrent processing by partitioning the problem data. Thus, scalability can be quite limited by unbalanced computational loads resulting from poorly partitioned data. The size of graph structures may also be a challenge during concurrency processing. In actual situations, graph structures are really large. For instance, Facebook Social Graph has more than 700 million users with 68 million relationships, while Twitter Social Graph has billions of follower relationships. With the graph structure so large, MapReduce might not be a good method to process these large graph structures when it is done iteratively, as it incurs a large amount of I/O cost. This slows down the processing and makes scalability a problem in the future.
In order to try to optimize graph processing, a type of graph processing architecture was developed by Google in 2010. Apache Giraph is an iterative graph processing system built for high scalability. It leverages on the Hadoop framework to iteratively process graphs. It is currently used at Facebook to analyze the social graph formed by the users and their connections. So how exactly does Giraph work? The main concept behind Giraph's processing algorithm is the bulk synchronous parallel. The bulk synchronous parallel, known as the BSP, is developed to solve the problem of parallelizing jobs across multiple works for scalability. BSP computation consists of a sequence of supersteps with synchronization between workers occurring at superstep barriers. A superstep, in this case, consists of a unit of generic programming that makes parallel processing on a mass of data and sends it to a meeting point, called synchronization barrier. At this point, the data are grouped and passed on to the next superstep chain. One of Giraph's advantages of using BSP is that the input graph data is loaded once at the start of the program, and all computations are executed in memory. The program keeps the memory there throughout the duration of an analysis job. Therefore, iterative algorithms that consistently reference graph data run faster by not having to access them from disk. However, it comes with a trade-off. The trade-off is that the size of the graph that can be processed by Giraph is limited by the total memory in a cluster. Another limitation of using Giraph's BSP is that workers can encounter the straggler problem, where faster workers must wait for the slower ones.
Next, Zhi will lead us through a demonstration of Giraph.
Before we start off for Giraph, we will be downloading the requirements. Firstly, we will be using Ubuntu server, not the client, as it will be able to load faster. Next, we will need Hadoop. Giraphs run on the older version of Hadoop, so we need to download the version from the archive. Other components like Java, Maven, and lastly Giraph we can download in the server later. As you can see, we will be using VirtualBox as the VM to start our server, using the default setting and enough RAM to load our virtual machine. Once done, you should be able to see your home screen like this. Select all the default settings. Name your username and password HDuser for simplicity. Afterwards, select OpenSSH to download as you will be using that later. Finally, reboot your server. Before that, change the network option. Make sure you are using the NAT and add the following port forwarding rules. Then start the server again. Now, log in with HDuser and generate your SSH key. After that, apt-get to get your update on your packages. Now, download the Java package. Once complete, check your Java version to ensure that it is correct. Now we add Hadoop into a group so that it has root access. Now we wget to download Hadoop. Once done, we direct ourselves to the configuration folder. Here we will make a couple changes to the configuration file. The first file we'll be changing is the call site XML. We'll add in the directory of the Hadoop and the temp location. Next, we'll be changing the map reduce site XML. Here we'll add in the tracker and then also the maximum number of tasks that we'll be running and the number of tasks. After which, we will be changing FDS site XML. Here we'll add in the requirements to ensure that two mappers run as one. To start Hadoop, first we format the name node, then we start the DFS and MapReduce shell file. You can use the JPS to see whether the service is running. To test whether it's working, we download a simple text file. We're able to run a word count method by Hadoop. Here, you're able to see the progress using browser by SSH. Finally, when the MapReduce is complete, you'll be able to see the output in the server. To get Giraph going, we'll be downloading Git. Once complete, we will download Maven. Once the download is complete, check that Maven version is more than 3. After that, we do a download clone for Giraph from Git. Lastly, we install Giraph package with Maven. Do note that this whole process will take a very long time. Now, we are finally ready to go. We'll be creating a tiny graph text file to represent a directed graph. Next, we'll run the shortest path code with Giraph to generate the shortest path. Once the MapReduce is complete, you are able to view the output from the server. As you can see, the interpretation of the output will be the node and its distance from that node to node 0, and the right side is the value of the distance. And that's all for our demonstration. Thank you.